Hi, I'm Young, and today I'll be talking about this paper. It's the paper that first suggested the quantum approximate optimization algorithm. And today I'll be giving you some definitions and then some connections from QAOA to the quantum adiabatic algorithm. And then we'll be going over one example for one example problem called max cut. And then I will finish off with some summary and closing remarks. Okay, so in the first section, we want to know what the quantum approximate optimization algorithm is. And we also want to know what kind of problems it can solve. So let's answer the second question first. We can define a combinatorial optimization problem as follows. Let's say that we have n bits, and we can each zi is a bit, and the whole collection of z1 through zn, we can write this as just bold z. And let's say we have m clauses, and each clause is like a constraint, and this constraint is only on a subset of bits, and this constraint can be satisfied or not satisfied depending on the values of each bit. So we can write this like a function. So let's say we have c alpha z, and this represents the clause alpha, and this function will return value 1 when the bits satisfy clause alpha, but it will return 0 if it does not satisfy this clause. Then we can define a max set problem. So like the name suggests, we just need to satisfy most of the clauses. And so the problem is we want to maximize CZ, where CZ is just the summation of multiple clauses. And actually, this is NP hard. So QAOA is algorithm that tries to approximately solve this optimization problem. So I will be using QAOA instead of our quantum approximate optimization algorithm from here on. And in order to define this, talk about this algorithm, we need to define a couple of things. So let's say that we have an n-qubit system, just like the n-bit combinatorial problem we had before. Then we can define the computational basis, and each computational basis can be represented as a bit string, so we can write it as follows. And we can define these two Hamiltonians. So the first one is C, where the eigenvalues is CZ, and the eigenvectors are just the Z vectors. So this is just exactly the it's like a Hamiltonian version of the summation of the clauses that we had before. So using this Hamiltonian, we can use this as a generator for a rotation. So we can define unitary as follows. So it's just simply just the rotation caused by this Hamiltonian with angle gamma. And we can write it as follows. And we can also assume that these C alphas all commute with each other. So we can write this as follows. Then we also need to define this B Hamiltonian, which is just simply the summation of the Pauli X the Pauli X's. And we can also define the rotation caused by this Hamiltonian as follows. Here we generally use the angle beta, and we will keep this convention later on. So please take note. And so we can also just write this as the local rotations of caused by Pauli X on each qubit. And for QAOA, our initial state is just the equal superposition of all of the computational bases. And actually, this is the ground state of B. We can check that. And we can also define the state gamma beta. Here, gamma and beta are vectors, and this is just simply S acting upon S, and then we act upon it using rotation by C, rotation by B, and then so on and so forth. But we changed the rotation angles here. Actually, I think I made a mistake. There shouldn't be 1 here or P here. It should just be the same. But the rotation angles can be different. So here we just write the whole rotation angles as boldface beta, and then same thing for gamma. So once we have this state, then we can define the expectation value of the cost. And we call this FP gamma beta. And note that there's a dependence on P because that determines how many U's we apply on S. And then we can maximize this value, and then this maximum will be called MP. And one thing that we need to note is that actually MP is larger than or equal to MP minus 1, because in order to get MP minus 1, we can just let all of the beta P and gamma P be 0. Then we can see that that is just simply equal to MP minus 1. So hopefully these definitions are clear. Then we can create an algorithm to find an approximate solution to a combinatorial problem. So let's say that we have a max set problem. Then from this problem definition, we can pick an integer p. Actually, this is not from the definition, but we can pick an integer p, and then we can construct the C and B Hamiltonians. And then from this, we can create the rotations caused by these Hamiltonians, so UC and UB. Then using this, we can find the gamma and beta values that maximize this FP value. And so this will give us our MP, right? And then we can measure this resulting gamma beta, which maximizes FP, in the computational basis to get a bit string. And then we can use this bit string to evaluate CZ. So we repeat the previous step multiple times. So we measure this gamma, we prepare this gamma beta once we know the optimal gamma beta. And then we measure it in the computational basis, and we repeat this multiple times. And then every single time we get a bit string, and then we calculate the cost and see which is the best bit string out of all of them. And so the resulting bit string, which has the best performance, is the approximate solution to the max set problem. So QAOA, this is the basic overview of what the QAOA is. And actually, when I first encountered this algorithm, I didn't understand why it worked. Like, I guess you can kind of do this, but why do we have to use the B and C operators? I was very confused about that. So actually, this paper goes into detail about why this works. And I think like one of the major points is that is the connections to the quantum adiabatic algorithm. So this is what I'll be talking about now. And before that, we need to know what the quantum adiabatic algorithm is. And before that, we need to know what the adiabatic theorem is. So the Schrödinger equation defines the time evolution of quantum states, and it's written as follows. And let's say that we have a time-varying Hamiltonian, and let's say that we normalize the time scale so that this time just changes between 0 and 1, and we'll write this renormalized type of Hamiltonian as just H tilde, and then the eigenvalues will change over time because the Hamiltonian changes over time. And here, this L is, if L is 0, then that is the ground state, and if L is 1, then that is the excited state. But the state will change depending on time because the Hamiltonian changes depending on time. Then the adiabatic theorem says that if we have an initial state, psi 0, which is the ground state at time 0, and large T is much larger than some value, then the overlap between the final state and the ground state of the final Hamiltonian is arbitrarily close to 1. So basically, if the starting state is the ground state of the initial Hamiltonian, and if we change the Hamiltonian in quotation marks slowly, then the final state will also be the ground state of the final Hamiltonian. So this is the adiabatic theorem. And so we can use this to do some calculations, and this is called quantum adiabatic algorithm. So let's say that we create some initial Hamiltonian which has a ground state which we can easily prepare, and we have a target. We have the final Hamiltonian which has the ground state that encodes the solution. So we want to change from this easily prepared ground state to the solution state. Then we just simply find some strategy for time evolution from the initial Hamiltonian to the final Hamiltonian, and we find the time. we find the time to keep the adiabaticity condition, and then we prepare the initial state of the we prepare the ground state of the initial Hamiltonian. Then we apply the Hamiltonian, but we change it in our strategy so that the final Hamiltonian is the one we want. And so we evolve the initial state using our prepared HT, and then we measure the final state to get the solution that we would like. So hopefully this is clear to you. So using the adiabacity theorem, we can cleverly create a situation where the ground state of the final Hamiltonian is the solution state that we want. So actually, we can see that QAOA can be an approximation of QAA. So let's compare the elements of our quantum algorithm. So there is the initial state. And we can see that for QAOA, this is just the uniform superposition of over all of the computational bases. And for QAA, it is the ground state of initial Hamiltonian HB. And the thing that we can note here is that S is simply the ground state of this B Hamiltonian. And we will later see how HB and B are related. And then for the time evolution for QAOA, we repeatedly apply this UC and UB. And for QAA, we just do the evolution by HT, where H0 is the initial Hamiltonian, but the large T is the Hamiltonian with the solution state as the ground state. And actually, by using trotterization multiple times, we can see that the evolution by the time-varying Hamiltonian in the QAA is simply just applying UC and UB multiple times. So you can see that this is UB and this is UC. And of course, these angles are just hyperparameters that we can change, parameters that we can change for the case of QAOA, but we can find values that well approximate QAOA to QAA. So we can see that QAOA can be an approximation of QAA. And if we look at the result, we can see that the parallels go all the way. So QAOA gives an approximate ground state of the C Hamiltonian, and QAA gives a ground state of the final Hamiltonian. Okay, so we can see that QAOA can be an approximation of QAA. Then I guess the natural question to ask is, why use QAOA over QAA? Well, QAOA has this property. I think that I said in my previous slides that this is important, but QAA doesn't have this property. So even if we increase T, large T to infinity, it doesn't. There are some cases where this isn't always. This doesn't give a good success probability. Okay. Now I'll quickly go into max cut. I think that I'm kind of running low on time, but yeah. Okay, so let's say let's consider this problem. We have some input graph. So we have vertices and we have edges, and we want to maximize this cost function. So this is just simply how can we make a cut that cuts through the maximum number of edges. So for example, if we have a graph like this, then the maximum cuts are shown here. So we can cut through all of the edges except for one. And these cuts can be encoded into quantum states or bit strings as follows. So we just label each node, and then we can say that each node is either inside or outside the cut. And so we can represent these two cuts in these 4-bit strings. And actually, we can formulate this C into the C Hamiltonian by just simply changing the ZK to the Pauli Z. So how can we solve this example then? If we think about the whole QAOA method, then I guess the part that is the most unintuitive is how to find the gamma and beta values that maximize the FP value. And one way that we can use this is using gradient descent. So I simply ran one of these examples. I just used the example from shown in the previous slide. I chose p equals 3, learning rate is 0.1, and then this cost function. So we want this cost function to decrease rather than increase. And this is the learning curve. This is actually a video. So this is the learning curve, and this is the measurement probability. And let's see how the measurement probability changes as the cost changes. Okay, so we can see that when the cost is lowered, the success probability increases. And so we can kind of see how this QAOA can be used to find a approximate solution to max cut. So using the state that gives these types of measurement probabilities, we can measure this state multiple times to find the correct answers with a high probability. But if we look at the so if we look at the initial state, so this is without optimization, we can see that even if we measure this state multiple times, the probability of us getting the correct answers is very low. So this is how QAOA kind of works. And okay, I'll try to go over this really quickly, but this is one of the major theoretical results of QA of the paper. So let's consider one layer QAOA on the max cut of 3 regular graphs. So 3 regular graph is a graph where all of the nodes have 3 neighbors. And first, in order to talk about this situation, we need to know about the properties of this value. So we basically want to know the properties of the expectation value of one of these terms. So if we write down this QAOA algorithm in a circuit format, you can see that it goes in like this form, in this way. And so we prepare the initial state, then we apply UC, then we apply UB. But we need to note that since all of the terms they commute with each other, we can simply just change the order like this. And let's say that we want to know the CJK of this edge. But the thing is that we can see that actually not all of the edges contribute to this term. Actually, only this edge, and this edge contributes to this term. For this edge, it doesn't contribute because these aren't measured anyway. So qubits with distance p or less, only the qubits with distance p or less in the problem graph contribute to the term. So hopefully this is clear to you. So if we have only p equals 1, then only qubits that are 1 or 0 distance from the target edge contributes to the term. Then for 3 regular graphs, actually there's only 3 different subgraphs. So for an edge, there can be only 3 different cases when we consider just one distance. And we will call this G4, G5, and G6. So actually, since the value only depends on, of course, gamma beta, but the type of the subgraph, then we can write down this the whole f value as just the number of each subgraphs multiplied by the expectation value of each subgraph. So now we want to know how many of each subgraph exists. So now let's consider different subgraphs of the total graph. So let's think about isolated triangles and cross squares. Now these are just some names that are given to these types of subgraphs. And we can actually see that since this is a 3 regular graph, these two can't share vertices. If they share vertices, then that means that there exists a vertex with more than 3 neighbors. So this means that 3t, which is the number of nodes in each triangle multiplied by t, and then 4s, which is just 4 multiplied by the number of squares, it must be less than or equal to n because they can't share vertices. Okay. So let's consider a case where there is a graph with these types of subgraphs, and of course there can be other types of subgraphs. And considering each edge, we can see which type of subgraph each edge is. So if you consider this edge, then there is a neighbor here, there's a neighbor here, but they share a neighbor here. So this is, in fact, this subgraph. So if we just go over each edge and see which type of subgraph it is, we can see that for each triangle, there are 3 G5s, and for each cross squares, there is 1 G4, which is this one, and 4 G5s. So this means that if we have a graph with T isolated triangles and S cross squares, then the number of G4s is S, the number of G5s is 4S plus 3T, and then the rest should be G6. So actually, this means that we can calculate this M1 value, but this M1 value, when it is determined, when it is parameterized by N and S and T, because we can just calculate the C values. Of course, it'll be quite tedious, but we can calculate this. Now we want a bound for the actual best cut. So we want to compare how good the QAOA algorithm is by giving a bound on how well the QAOA acts, and then also a bound for the actual best cut. So if we consider each triangle, we can see that there is at least one unsatisfied edge. So there can be this type of cut, this type of cut, or this type of cut. But in each case, there is always one unsatisfied edge. Note that this is not a cut, because this goes through this edge 2 times. And for the square, it's the same thing. There must be always one edge that is unsatisfied. So, for example, this is this is one cut, but this gives this one unsatisfied. So we can see that the actual solution, which is the bound for the actual best cut, must be lower than or equal to the total number of edges minus T minus S. So using these 2 inequalities, we can make a bound for the approximation ratio. So we know that the QAOA solution must be larger than or equal to M1. And we know that the actual solution is less than or equal to 3n over 2 minus T minus S. So if we just simply divide these 2 terms, then we can see that the right-hand side is a lower bound. And actually, we can find a lower bound of this lower bound, which is 0.6924. So we can see that actually QAOA has a performance guarantee for certain problems. So if we get a QAOA solution using P equals 1 for max cut on 3 regular graphs, which I admittedly is a very specific problem, we actually have a guarantee for the approximation ratio. And actually, the authors of the paper did the same calculations for P equals 2. And in that case, the approximation ratio increased to 0.7559, which is good news. And actually, the authors also did similar analysis on another type of problem in the paper. But one bad news is that the actual best performing classical algorithm has approximation ratio of about 0.93. So we can see that actually QAOA for very low P is not very good compared to classical algorithms for max cut. And now I'd like to finish up with the summary, and hopefully I can summarize what we've learned today. So the quantum approximation, the QAOA algorithm gives approximate solutions of combinatorial problems. And we know that higher P gives the same or better results than low P results. We know that QAOA works because it can be an approximation of QAA. And also it has performance guarantees for certain problems. So this is the main points in the paper. And some things that we can think about is that actually optimizing these parameterized circuits that the QAOA suggests that you do is quite difficult. Actually, it's known to be NP hard. And so the question is QAOA worth it in this case? And also another problem is that we saw that for max cut and on 3 regular graphs, the P is pretty low compared to classical algorithms. So, and also, so we want to increase we want to increase the approximation ratio, but the problem is that we don't know how this approximation ratio improves with respect to P. This is, as far as I know, an unsolved problem. So hopefully I've given you an okay introduction into QAOA. And yeah, that's it. Thank you.
Any questions?
Thank you for your question. Actually, I'm not really aware of many types of problems that have a performance guarantee. But as you can see for these three regular graphs, we can kind of change the problem into another type of problem which we can kind of solve analytically. So maybe if it's a problem where we can change the initial large problem into just many small problems, then maybe that is one characteristic, but I'm not aware of, actually, I'm not really aware of other problems other than max cut and the ring of disagrees in this paper that has that type of guarantee.
Which one should try is to comparing the QA wave and QA? Yeah. So I'm not really not aware of what is the QA wave, but can you explain why the initial state of the QA wave is, I mean, the computation basis, but how can it be matched to the initial state of the Hamiltonian QA wave?
Now, okay, thank you for the question. So, I guess one way that we can do is first, let's think about the time evolution. So let's consider the evolution of a quantum state caused by a time varying Hamiltonian where the initial Hamiltonian is called HP and the final one is HC. Then we can actually write it and then we can approximate it into this form. And this form is actually just simply each of these Hamiltonians acting it's the rotations caused by each Hamiltonian acting just one by one, just in succession. And we can see that actually this is very similar to this form, which is the form of the QAOA. And since the QAA, and so we can draw parallels from that here. So we can see that we can kind of think that maybe there is a connection between C and HC, B and HB. But the parallels go even further because the initial state to this one, which is just we can factor this out into just plus states, right? It's just the product of plus states, and that is exactly the ground state of this B Hamiltonian. And also the resulting state is the ground state of C, approximate ground state of C. And for the QAA, it is also the ground state. Of course, this can also be approximate, but yeah, approximate ground state of the HC. So yeah, we can see that the QAOA and QAA is very, very closely connected. Thank you.
And you said there's a mathematical guarantee. So the author just assumed that maximization is possible without any like stuck in the local optimum, for example.
Yeah, the authors didn't consider about the optimization process. They just assumed that, I guess the part where I can talk about that is actually here. So this M1 is kind of like a theoretical maximum, but we assume that the QAOA solution can be, if the optimization is, it doesn't actually even need to be perfect, but if it's good enough, then we can get a bit string which is larger than this mean. Since this is like a mean, and this can contain even the probabilities for non-solution bit strings. So this will be lower than the actual solution. So we assume that the QAOA solution is larger than this one, which means that we have a good enough maximization. Yeah, which I think is a pretty big problem because we want to optimize PQCs, which is difficult.
And this is a really unrelated question, but when you compare QAA and QAOA, there's a curly tree T, which is called time ordering operator.
Oh.
And I didn't really understand how it works. I mean, but I know what it's supposed to mean, but how does it? Do you know how does it work in mathematical ways?
Ah, I think you're going to expose my lack of knowledge in mathematics, but I think, so isn't it something like this? I'm not, I always forget, but isn't it something like this? So I think that it's called time ordering because there's this ordering between T1 and T2 for high order terms. Is this kind of distinction now in my process? Yeah, I think that there's like a problem if you just don't have this condition and you just do 0 T. I think there's a problem with the first. Yeah, higher order term would be like I think so. I'm not quite sure, but yeah, I'm not. So actually, my answer would be I don't know. But I think it's this, but I'm not quite sure.
You write down the quality is exponential.
Yeah, but
Right.
so if you're asking about the how we can get the approximation from this one to the next one, I think I looked at the proof once, but I'm not really sure. But the second one we know about. That's just the processes.
Thank you.
Sorry for the for the incorrect answer.
Okay, any more questions? Okay, then thank you for the presentation and